8.5 question 1. Is that the one I'm showing you? Is it that one?
Yeah, sorry, it was the I think it was the part C on that.
I have a part C on question 1. Well, I do have this thing down here, the sample test statistic. Is it that one?
Yeah, that one.
Okay. Now, it's a t-distribution, right? And you'd probably have to look up the notes, because when we do t-distributions, don't I just go straight into the calculator? I don't do it by hand. But if you were doing it by hand, the one that you would be using would be this one here. So it should have been the fourth one. So if you're getting it wrong, I'm assuming it's because you picked one of the others. Right. It's just a formula that you would find. I guess I could explain it a little bit. Isn't x1 bar take away x2 bar the difference between the two means? That makes kind of sense. And that horrible mess on the bottom is the standard error for a t-distribution. And you notice that it uses the sampling standard deviation. It doesn't use sigma, because you don't know sigma in those questions. So that's why it's number 4.
While you have the homework up, I actually have a question on 8.3.
I am going to go into 8.3 now.
And not particularly like a
specific
question,
right.
But there's a few questions that have what I'm confused about. So, for example, number 4 has it.
Okay, if we hold on, it's loading. I got 4. Oops, no, I picked 5 by mistake. Oh, it's a long question. Okay, I got 4 here. Right, now I may have to, I don't know, can you see 4 now?
Yes, now I can.
Oh, good, it works. Sometimes it doesn't do that. Right, so what was the part?
If you scroll down to the sampling distribution, I was confused why the area shaded in for the p-value is only until it like stops at -3 and 3. Like those are the boundaries. I thought
are you
there
talking
probably
this
shouldn't
answer
be
here?
Boundaries. Yeah, or any.
Okay,
any
so
of them.
Right. So in this story, there's a H0 and HA, so or they call it H1. So it starts there. So we have to figure out what that story is saying. So this is something to do. Bernford's law claims something to do with if you take a large number of figures, a lot of them start with the number 1 more than any other digit. Then it says a lot. Millions in terms of the phone, and it's either just the periods important numbers of right.
Yeah, my question isn't exactly about. I know how to do the problem and what sampling distribution to shade.
Yes.
But I guess I was confused why on the sampling distribution you have selected. Oh no, it's actually. I think it's the one to the right. But why the value shaded in for the p-value stops at -3?
Well, if it's this one here, it stops at -2.8. Oh, why does it finish at 3?
Yeah.
I mean, it doesn't really. It keeps going forever, but the picture stops somewhere, so it stopped at 3.
Oh, okay. I remember when I was scrolling my mouse over the homework, it said it stopped at 3, but I guess that's just the way.
Yeah. I think when you put your mouse over it, it tells you things. It's for people who have visual issues, and so that would read out the number. That's so that the people can get an audio version of what the picture is saying. It doesn't stop at -3. It goes on forever.
Okay. That's what I was.
But you got to imagine, you can't draw a picture forever, right? So you got to stop somewhere.
No.
I think the reason they stop at 3 is if it's bigger than 3 or less than -3, aren't you probably in the places where it's going to be significant?
Yes.
Yeah, I guess it could have stopped at 4 if they felt like it, but they didn't.
I also have a question for that same question for number B. The second part where it says, you know, we know which one to pick if it's standard or if there's sigma is known, but what's the NP greater than 5 and NP?
Right,
Yeah.
that is the condition that allows you to even start the process. It says, look, don't even try this unless your sample is big enough. And they don't do it by, oh, the sample has to be bigger than like 33 or so. They use a condition called NP and NQ. Q is the same thing as N1 minus P, by the way, right?
Okay.
So N, the size of the sample, times P should be a number greater than 5 if you're going to be able to use this.
Okay.
And so should NQ. It really shouldn't be 5, you know, it really should be 10, but this book's funny, they call it 5. And what that does is basically, don't do a sample of 3 people and ask them, because NP won't be big enough. Don't do a sample where P is so tiny that NP is less than 5 as well.
Okay. So it always has to be greater than 5.
Yeah. The way I look at it is NP is the number of people who said yes, and NQ is the number of people who said no. So when I'm looking at a sample, if 42 people said yes and 53 said no, I'm cool with that. If 4 people said yes and 7 people said no, I'm not cool with that. That's not going to work. Because 4 people saying yes is the same as NP. That's what NP is. It's how many people said yes. So that's kind of how I look at it. How many said yes? How many said no?
Okay, yeah, I forgot what that was, and I'm like, I know it was normal, but I didn't know the second part. Thank you.
No problem. Are we good with this anymore before we close these windows off? I'm getting good questions, but okay. Let me try and close off the many windows I've got and got the right one. Good. We are going to look at, get somebody in the chat. Oh, somebody's saying me, thanks. Right, we're going to look at 9.1. I have no idea where I am right now, which is kind of a permanent feature for me lately. All right, we're going to do 9.1 scatter diagrams and linear regression. So I want you to imagine that you had a table, because very often it comes from a table with 2 variables in it. And the top one could be someone's age, let's say the age of an animal. And the second one is going to be the height, or the height or the length of an animal. And so it's 1 month old, it's 2 month old, it's 4 month old, it's 6 month old, and it's a year old. And you collect some data and you get its height. And this animal, when it's a month old, its shoulder height from its shoulder to the ground is 5 inches. And then it's 8, then it's 12, then it's 15, and finally, what will it be? 23. Now, from this table, we're going to create what's called a scatter diagram. You got to just imagine that I'm doing this really neatly, and I was doing it in square paper. But the x-axis is basically going to be the age of the animal, and the y-axis is going to be the height of that animal. So I would have a scale from 1 to 12. So 1, 2, 3, 4, 5, 6, 8, 10. Right, there's my scale going that way. And I need 23, so what shall I do? 5, 10, 15, 20, 25. Some kind of scale like that. So what does a scatter diagram look like? It's really just plotting coordinates. So at the age of 1, it was 5 inches tall. So an age of 1, it would be about here, right? At 2, it got to 8, which is probably about there. By 4, it was 12, which would take it to about here. 6, it was 15, takes it about here. And at 12, it's 23, which takes it about here. And I'll make these dots extra big just so we can see them. And that's what a scatter plot is. It's basically doing a visual representation of a table. Now, when people look at numbers and when people look at pictures, would you agree that pictures are just easier to see what's going on? For instance, in this particular question, would you agree that although it's not a perfect fit, aren't those dots pretty much, my pen almost does it, doesn't it? Aren't they pretty much on that straight line? Now, when data is in a straight line, even if it's approximately straight, right, then we call that relationship, we call it linear. We say that the data is linear. Okay. Now, let's look at big picture stories. Linear. Curved. Random. Can you imagine that certain data, when you plot them as linear, right, it's roughly straight lines. Can you imagine other data, it's not perfect, but it's a curve, right? And can you imagine other data where there's no particular rhyme or reason, right? The data is just totally random, right? The scatter plot, no discernible relationship, right? So we can describe scatter plots by saying they're linear, they're curved, or they're random. Now, within linear, can you imagine a set of data points that, although not perfect, are very close to being a single straight line? I'm going to put a couple of dots down here, right? We would say that was a strong relationship or a strong correlation. If a straight line had data that was linear, but would you agree that it's much more spread out, as in this picture, then we would say that it was moderate. And if you had a linear, I guess I'll stick the word correlation. And if we had, yes, it is linear, but, you know, even worse looking than that one, then we will use the term that it's weak. So we're only looking at really linear scatter diagrams, right? Data that looks like a straight line. And that's the one that we're going to focus on in 9.1 and 9.2. Strong, moderate, weak. That's one of the terms. So now, you can have linear data that goes uphill, and when it does that, we say that it is positive. But isn't it just as likely that you could get data that's linear, but it goes downhill, in which case you'd call it negative. Those terms, positive and negative, aren't arbitrary. I mean, there is a reason behind it. Would you agree that that line has a positive slope and this line has a negative slope? That's essentially why it's called positive and negative, right? Linear correlations. So you can have strong, moderate, and weak. You can have positive and negative. If the data looks like it's going uphill, it's positive. If the data looks like it's coming downhill, it is negative. You can actually have, well, let's put it together. Couldn't you have positive and strong, positive, moderate, and positive, weak? Negative, strong, negative, moderate, negative, weak, right? And you can also have this. let's call that positive and moderate, right? Would that seem reasonable? Positive and moderate. And then you have a guy down here, sticking out like a sore thumb. We have a name for data points that stick out like a sore thumb.
Is it an outlier?
And it uses the same name. And it is. That means then that I should be able to describe a scatter plot by words. So suppose I went and said to you, it was a strong, negative, linear in shape. So I'm just giving you 3 words. It's strong, it's negative, and it's linear. Wouldn't it probably look like that guy? That makes sense? So you'll be given very simple questions like, here's a picture. Is it positive? Is it negative? Is it strong? Is it weak? You probably won't be asked if it's linear because all the questions are going to be linear for the most part, right? And so you would be looking at that. I don't think they mention outliers as a pity because it's a good thing to know, so I've told you anyway, right? If you do have an outlier, and do you know that it's going to screw up your numbers, your statistics? Do you know that the equation of that line that I've just drawn is unique? In other words, there is one line that is a better fit to the data than any other line you could draw. So you might think, well, can I draw a line a little bit lower, a little bit here, a little bit up here? Well, you could, but there's one line that's considered the best and it's unique. And it's called a number of things, but this textbook calls it the least square line. Me personally, I like a name that you're going to probably see if you go looking for it. It's called the best fit line. I just think best fit makes more sense than least squares, right? Does best fit kind of give you an idea what it is, right? It's a line that's the best fit. But it's just a name, right? That's what we call these lines. We are going to look at a very special number, and this number is called the correlation coefficient. And everybody, including thankfully this textbook, uses the little r for it. And the correlation coefficient is a number that tells you how good the data is to being a straight line. And it only takes a range of values between -1 and 1. So let me show you what that would look like. If you had a perfect straight line, which I'm trying my best to do, that would have an R value of 1, right? A correlation coefficient R equals 1. What do you think the R value would be for a perfect fit?
-1.
Now, what do you think they would call a random set of dots? What kind of R value do you think you would get for that?
0.
0. Can you see then that the R values range between perfect straight line on one side, perfect straight line on the other, and everything else in between is like a kind of sliding scale of how close you are. So for instance, if you had a scatter plot, wasn't perfect, but was darn close to being perfect, right? Something like that, like this one here. You could get an R value of say 0.9 out of it, right? Can you imagine one that's maybe not quite as good, but still positive, right? So maybe, you know, a little bit like that. That might have a value of say 0.6. If you get kind of the next level, can you imagine one that's just about linear? Right, I mean, it still has that linear shape to it, but you agree the dots are like all over the place. That guy might be 0.3. So can you imagine that a strong would be 0.9, a moderate might be 0.6 or 7, and a weak could be a number like 0.3? Do you get a kind of visual, kind of semi-idea of how close the dots are to being perfect? Is a relationship that is how close is this number to 1? Or -1 if you want to slope down the way. Now, right now, I'm just bringing this number out of the air, right? I'm saying, oh, this line is 0.9 and this line is 0.6 and this line is 0.3. This helps me, I guess, because I'm a visual person. This doesn't exist as far as I know in a textbook. But if I'm trying to judge straight lines and how good they are, I do the sausage trick. Fat sausages are weak. Medium sausages are medium, and skinny sausages are strong. Some people need to put borders around things. It kind of helps them see, right? You might not. I just, you know, because I've got a visual brain, I can just imagine the sausage. It's not physically there. I can just imagine what, yeah, that's probably. So I think, when I think linear, I think of little, you know, a band, like a little railway line. If they're really within the same railway line, that's a strong, right? If you move it a bit bigger, isn't it going to be moderate? If you move it, you know, a lot away, it's going to be weak. And that's a kind of very crude rule of thumb for what kind of strength does your linear relationship have. Are we good so far? Now, you can calculate this R value from your data. You cannot do it by hand, at least I wouldn't, but you can do it on the calculator. So I'm going to take this data set and I'm going to calculate its R value. And first thing I'm going to show you is a nuisance, but once you've done this, you only do it once. The calculator default factory setting does not include what's called diagnostics on. Diag on. Diagnostics on, I don't know why it's called that, but it needs to be on for us to be able to calculate R. I think it's just a big mistake by them. I think they should have fixed it, but they never did. You know, the chips had already been produced, so they're not going to recall all your calculators just to fix this. So what we're going to do is we're going to set this to be on. So down at 0, do you see there in blue it says catalog? Go blue button, catalog. And in this menu is every single thing that the TI-84 can do. Right now it's got absolute value. If you can't find something, it's always going to be in catalog. If you really can't find what menu inside what other menu is something hidden, you could do this. We're going to scroll down by hitting that button until we get to the D's, and in particular, diagnostic on. I'm getting close. Oh, perfect stop. Do you see it? Diagnostic on. Got that? On my screen, diagnostics on. Hit enter and hit enter, and it's done. If you've done that with me, you've done. You don't need to do it again. It's now fixed forever, right? So I promised you that I was going to be able to get the correlation coefficient, right? That magic R number from this set of data. So first thing I'm going to do is hit start, and I'm going to do edit. It's not a surprise. I don't think it's a surprise anyway. Sugar and spice. I hope I didn't kill this. Okay, we're good. It's not a surprise. Shouldn't we be putting this into the calculator, right, the data? the top row is going to be your x's. So that's going to be 1, 2, 4, 6, and 12. The second number is going to be the y's, the height. So in this case, 5, 8, 12, 15, and finally 23. Yeah, we've done that for all sorts of other reasons, right? This section has got nothing to do with hypothesis testing or anything like that. This section is to do with the relationship between two variables and how they're interconnected in a linear way. So once you've done that, you hit Stats, Calculate. So Stats button, Calculate, not Test menu, Calculate menu. It's been a while since we've done Calculate menu. Can you remember week 1? Isn't that where standard deviations are? If I gave you a list of numbers and say, find the mean and standard deviation, wouldn't it be number 1 that we just? Now I want you to scroll by linear regression until you get to linear regression A plus BX. Then you hit enter. Now, in my calculator, I have to tell it L1, L2. You might have a modern one where L1 and L2 are there, in which case just hit enter, enter, enter. I have to do it slightly clunky way, but there's L1, there's L2. Now, in this...
Wait, how'd you do that?
How did I do what?
Put the L1 and the L2 up.
Okay, let's show you that again.
Yeah, I see it.
Oh, you see it?
Yeah. And you
Okay.
just put L1, L2?
Yeah, you just do shift 1 gets you L1, comma, shift 2 gets you L2.
And do I need to comma them?
Yeah, you need a comma.
Okay, thank you.
Now, when you look at this, there's lots of stuff, but what we're looking at right now is, do you see that that R value is 0.99? Now, it might not look it to you when you look at my very badly drawn picture, but that is a pretty darn close to being a perfect straight line. You agree? It's almost 1. So that would be a really strong fit to being linear. Now, you got to take that with a pinch of salt. In real life, that's far too few data points. Give you an example. See if there's only 2 data points, won't everything be a perfect straight line? Yeah, but you know, there's a lot of variation in data, right? So we're going through the process, but just like in many of the questions that we have to do, for practical reasons, aren't the data samples much smaller than they really should be if you want good answers? But we'll pretend that we've got 500 numbers, we got good answers, right? So we got an R value. Even better than that, do you notice that there's a guy called A and a guy called B? You see it? A is 4.7, B is roughly 1.6. Right. Well, A is about 4.7 to 1 decimal place, and B is about 1.6. They also call this guy y equals A plus BX. Now that means 4.7 plus 1.6x. Do you know what you get from that is the equation of this line?
That equation looks really familiar.
Well, this?
Yeah.
I don't know why, but yeah, yes, it could be if you did.
Y equals mx plus b. That's
Yeah.
probably why it looks familiar.
It's a version of y equals mx plus b, but they
Okay,
switched the
that's
order
fine.
and they called it a and b. Right, that's all it is. But would you agree that is the equation they're like? If you were an algebra person, wouldn't you probably call it 1.6x plus 4.7? And I would, and a lot of textbooks do. But you know, the guy who did this just wants to do his own little thing, so we'll let him do his own little thing. He likes to put the number first and then the x is second, so you know, it works. Now, since we've got this question,
Sorry, I just wanted to make sure. I just got home, so I'm going to switch to my computer. So I'm going to log out, and can you just let me back in?
sure, I can do that.
Okay,
Now,
thank you.
if you have an equation of a straight line, what does the 4.7 call you? Think back to algebra. the 4.7 would actually be this number here, right? And it's called the
y-intercept.
Thank you. And what does that 1.6 get called?
That's the slope.
Okay. So this little funny menu that I've just given you, here we go, Kelsey, you're back in. I'll try that again. There we go. Don't you just get the correlation coefficient R? That's cool. And you also get the equation of the straight line. You have to kind of work on it, but you get the equation of the straight line. Pretty much everything you want to know there is in that page, isn't it? Do you know there's a guy above it called R squared? You see it? It's what, 0.98? You see that guy? R squared. R squared, in this case, it's 0.98, roughly. It's called the coefficient of determination. And although it's a decimal, we almost always think of it as a percentage. And what that tells me is another way of telling me how close this data is to being a perfect straight line. This is telling me that this set of data is, well, the jargon way of phrasing it is that 98% of the variation is accounted for by the straight line. Right? 98% of the variation is accounted for by that straight line. I guess if you were saying it in more English, it's a 98% fit. Right? So if I had some data and it was a 40% fit, would you feel comfortable that it was very good data? No, there's a lot of variation. It's be hard to use it to predict. But since I've got this equation, couldn't I use this equation to predict how tall this little animal was when it was 10 months old, even although I never recorded it? If I wanted to know how tall is this animal when it was 10 months old, wouldn't I just find y equals 4.7 plus 1.6x? Y would be 4.7 plus 1.6 times 10 months old. And that would be 20.7. So I would make the prediction that at 10 months old, that animal was 20.7 inches tall. And wouldn't that be probably a pretty accurate prediction based on the fact that this data is pretty linear? Will it be perfect? No, nothing is. But would it be close? Pretty sure it would be close. Are we cool with that? So we've got this new technique where you've got data that ends up being some type of line. We get an R value that kind of tells us how good a fit it is. You know, a number that's really close to 1 or -1 is a really good fit. We can find the equation of the line from our calculator, and we can use that equation of a line to predict what value a certain thing would be. Pretty cool.
Would you explain again the difference between R and R squared?
R is just another number that does the same job as R squared. If R is really close to 1, it's a good positive fit. If R is really close to -1, it's a good negative fit, right? R squared, because it's calculated. Oh, by the way, I might not have mentioned this. Do you know that R squared is what you get if you square this number? It's not just its name, it's what you do as well. Now, if you square this number, can you trust me, you get that guy, right? R squared does the same job. If R squared is close to 100%, doesn't that mean it's a really good straight line fit? And if R squared is, 10 or 20%, that's a pretty bad fit, right? So it essentially tells the same job. We like R squared because R squared is the same whether the line points up the way or down the way. See, if this was -0.99, wouldn't the R squared still be a 98% fit? So we tend to like that because it's easier in the brain. If I say 48% fit, 20% fit, 92% fit. I don't need to say negative 0.8 and positive 0.75, because some people who are not into statistics might think that a negative number was somehow a bad thing. Right, an 82% fit, you get a feel for it, right? R equals negative 0.75, you're not good. It doesn't have that same kind of feel to it, for want of a better word. Cool. Now, let's show you something that is a big problem with this. Correlation, which is just the fancy word for drawing a straight line through data, right? If you're doing a correlation, you're making the data linear and you're trying to see what it is, right? Is not causation. Now, what do I mean by that? In many cases, the reason we do this is because we believe the top variable, the guy I'm calling age, is a good indicator of what the height would be. In other words, as you get older, this creature gets taller, right? There's a direct connection, right? Age makes you taller, right? Older you get, the taller. Now, there'll be a limit to that. Animals don't keep growing for their entire life, right? Neither do we. Don't we reach 18 or so and we stop growing? You know, cats 3 years and they stop growing, whatever it is, right? Every animal has a kind of stop growing period. But as long as you are in that period, everything is fine. This is not always true. So I'm going to give you two examples, kind of silly ones, but silly ones kind of show the point, I think, of a straight line relationship where the x's are not the reason the y's. The x's aren't causing the y's. So here's the first one. Along the bottom, we're going to do the average number of televisions per household in a country. So if you went to a country and you went to a house, somebody's house where they live, or apartment, whatever it is, and you added up all the televisions, and we're including TV monitors, you know, as well, right? So TV monitors, you know, PC, computer monitors, TV in the bedroom, the whole 9 yards, right? And we have 0 TVs, 1, 2, 3, 4, and 5. And the vertical scale is life expectancy. So every country has a number, and basically what's the average life expectancy? How long does a typical person live in that country, right? And let's say it starts here at 40, right? We'll just do a scale at 40. So it was 40, 50, 60, 70, 80, 90, something like that. And you go and you collect data on America. How many TVs do they have in a household? What's the average life expectancy of an American? And you plot the dots, and you will get a positive linear relationship. So each one of these dots would represent a country, right? So, agree it's linear. Would you agree it's a pretty good fit, right? Pretty good fit. You know, moderate good, whatever you want to do. The big mistake is the final jump. How many TVs you have affects how long you live. Now, do you know if that was true, wouldn't people buy 20 TVs and store them in their garage so they could live long? If that was true, wouldn't America not send medical help or doctors or money to poorer countries to try and help their life expectancy, try to make the people in that country live longer? Wouldn't we just send them televisions? What is happening here is a concept called a lurking variable. I like that name. It's not one of my made-up names. It's a real name.
Is that different from a confounding variable?
Yes.
Okay.
So a lurking variable, I'll tell you what a confounding variable is as well. Although I don't think this textbook goes into it. So how do you know that term?
I was watching some of the videos that you posted,
Okay.
and
Right.
then he talked about it.
Okay. So we have a lurking variable first. Right. What do you think this is really measuring? It's not measuring how many TVs you've got and how long you live. What's this X scale actually indirectly a measurement?
Could it be the TV size?
Nope. Not this time. No. Nothing to do with the television size. Why do countries with lots of TVs live longer? Maybe I should ask the question that way. Zoe.
Because
Because they have
they're more wealthy.
more money so that they
Yeah.
can afford more healthcare.
And if you have more money and you can afford more healthcare, doesn't that make you also rich and you can afford more TVs? So would you expect a country that has lots of TVs to probably be a richer country than a country that has very few televisions? And so what this is really measuring is wealth. So the lurking variable is the real major connection, right? It's hiding in the background, and sometimes it's difficult to see. Now, in this case, I think everybody and their mother would say, yeah, TVs don't make you live longer. I mean, that's silly. But would you agree that being a wealthy country probably does help you live longer? Because wealth has lots of advantages to it. If a country is really wealthy, won't they have probably a lot of doctors, a lot of hospitals, access to the best in the medical care that money can buy? And indirectly, won't you have a safer lifestyle? Won't you have more food? Because some people, just having the right food is an issue. Won't you stay in nicer places so you won't get, living in a shack in the middle of -20 is probably not a good way to live long, right? So wealth is the main lurking variable. Here's my second silly one that shows you that correlation, a perfect straight line, doesn't mean that the x's cause the y's. In this case, the x's are TVs. That's not what's causing it, isn't it? The lurking variable wealth doing this. Now, here's my second one. I'm going to do the reading age, and along the x-axis, we're going to do the shoe size. And from my last class, nobody told me what the shoe size of kids are. So I'm just making up numbers. In this country, kids wear shoe sizes 3, 4, 5, and 6, right? Up to 10 years old. Do you know that you can have a test, a standardized test that does your reading age? So if you've got a 5-year-old kid, they can try the reading age, or if you've got a 9-year-old child, she might be reading at a 12-year-old age level, right? And if she is, you should be quite proud of her, because that means she's really good at reading, right? So they collected data on the shoe size of children, and they measured it against their reading age, right? So they read like a 5-year-old, a 6, 7, 8, 9, read like a 10-year-old. And the data is linear. So each one of these dots represents a child's shoe size and what their reading age is. Does that mean your shoe size makes you read better? Is that the cause? I mean, let's put it silly. See if that was true, right? See if the size of your feet was a direct reason why you read better. Can you imagine very bad mothers who've got children who are not good at reading, takes them into this disreputable hospital where they break their children's feet and they stretch them out 2 shoe sizes bigger, and when they get home they'll be able to read better? Because that's what you're saying, aren't you? If that's true, that shoe sizes make you read better, then all you need to do is make their shoe size bigger and they'll read better. What do you think is the lurking variable in this story?
Age and education level.
Well, we'll just keep it. I like the first one. Age will do. You're right, education level would certainly be true as well. But age would probably be a more general version, right? Isn't it true? Not totally true, that's why there's variation in this, but don't 10-year-olds have bigger feet than 4-year-olds? And don't 10-year-olds read better in general than 4-year-olds? So really, aren't you just measuring how old the child is, but you're doing it in an indirect way? Aren't you measuring how wealthy a country is, but you're doing it in an indirect way? The lurking variable is the real variable, right? The one that should have been here, the one that is causing that, right? Age is the main reason that you're reading. Don't most 8-year-olds have a reading age of 8? Most 10-year-olds have a reading age of about 10, right? It kind of makes sense. Your age and your reading age match well together.
One of those examples that I've heard that I really like is the number of ice cream cones sold in an area correlates to the number of drowning deaths. So, of course, ice cream.
That's a depressing one. So who did that one? The number of ice cream cones and the drowning deaths one. Who heard that come from?
It was just an example that came up in my political science courses.
I heard
I've
one
heard
like
of that one too.
Yeah, I heard that one, but it was with crime rates. Like ice cream sales correlates to crime rates. It was
Right.
weird.
So that is an example of this statement. Correlation doesn't mean causation. So it's kind of cool that you've seen it in other places. So it's nice to see that we share the same thought processes, even although I'm doing it from statistics and they're doing social sciences. In fact, a lot of social science stuff do statistics indirectly, at least. And when they did it, did they just tell you the numbers and go with it, or did they ever bother to do what we do and do it a little bit more in depth?
In the classes I took, it was just here's the numbers and then let's look at them, but we never did any calculating.
Does it help to see where they came from? I know it's past, but does it kind of say, okay, now I know why this was that number and not some other number? That's kind of cool.
I have a question.
Yes.
So on the top example, so even if we made wealth the x-axis, wealth still doesn't exactly increase life expectancy, right? But it's just more, it's correlated.
Closer.
Okay.
It's closer to the reason. I guess if I was trying to think of a better one, maybe I could figure out some measurement that would be closer fitting. But wealth is a pretty good fit because if you're really wealthy, don't the things that go wrong with wealth are the reason that your life expectancy is correct? So wealth is like a catch-all thing. We can measure wealth. Do you know gross domestic product is a good number for measuring wealth, which is basically, a better measurement of wealth is not gross domestic product, but gross domestic product per person, which basically means you take the entire wealth of what a country makes in a year and you share it out theoretically with everybody who lives there. And that number is a pretty good indicator of how wealthy a country is. And if you do that, you'll find out that there are a lot of countries in the world who have high wealth and have high life expectancies. It's almost you can almost guarantee it. It kind of makes sense. If you're in a really, really poor country where half the people don't even get enough to eat, you're not going to have a great life expectancy there, are you? Even if it's the prettiest country in the world, but actually a lot of them are, they're really pretty, and they just don't have any money. Mostly, well, not mostly, one of the reasons they don't have a lot of money is that very often in those same countries, don't they have a kind of dictatorial leadership that steals all the good stuff and nobody else gets it? That kind of thing. That's unfortunate. But those people live a long time, by the way, because they do have lots of money, right? And when they get sick, don't they go to France and get an operation, right? Or they go to America or someplace. But the normal Joe Blogs in those countries don't live long.
And then even if you insert the lurking variable into the x-axis, do you still apply the same guideline that correlation's not causation, even if the x-axis is more accurate?
When I say correlation is not causation, I should qualify that. It doesn't guarantee it.
Mhm.
So a good correlation is a good thing to have. And if you have a guy on the x-axis, it may be the major reason, right? All I'm just saying is that not always is this, you know, so it's a not always situation. Be in the lookout. Now, since you went and mentioned the other guy, correlation is not the same thing. Sorry, lurking variable, and you said confounding, right? Confounding variable. I think it was you, Rachel, right? Yeah. Okay. Give you a story because it's not connected to this. So I don't want to get too much into details. Can you imagine a professor was wanting to test his teaching style? This is a story that we use a lot for this. And so he decided in the summer quarter his teaching style was going to be very laid back, you know, not too stressed, tell jokes, do his thing. And then he would collect the data on how many passed and what kind of grades he got. And then in the winter, he became very formal and he wore a suit and he never told jokes and he becomes like a university, many university lectures are, and he'd done his same classes, right, different students, right, but the same classes, and he looked at the data. And he found out that the summer classes got much better grades than the winter classes. And he then made the false assumption it was the teaching style. But actually there are two variables and they're confounding each other. Because couldn't it be teaching in the summer, regardless of how you teach, people do better than in the winter? Because in the summer, he did one teaching style. In the winter, he did another teaching style. You can't separate out whether it was the time of the year or the teaching style. That's an example of a confounding variable, right? You're puzzled. You can't really separate it. Now, if he wanted to do that test, shouldn't he have taught one class in the summer informally and one class formally? And then in the winter, one class formally and one class informally? And then couldn't he separate out what the main cause for the differences would be? So that's what a confounding variable is. But you don't really think of them in this context, right? Lurking variables are in this context. That help? Okay. So let's look at some questions here. Some homework questions. So, oh, any questions before I go on, just in case? Okay.
Are you going to show us how to input the data on the graphs?
Am I going to show you how to input the data onto the graphs?
Yeah.
You mean in the homework here?
Yeah.
Yes. So hold on and you'll see that. So here is section 9.1 homework. It's scatter diagrams. I think its full title is scatter diagrams and correlations. So describe the relationship between two variables when this is true. If it is near -1, right? So if R is near -1, which one of these five, we'll call them 1, 2, 3, 4, and 5. Which one of those five would you be using to describe what's happening?
4.
Look really carefully. It says -1.
Weak negative linear correlation.
Okay,
The middle one?
so we're looking at weak. Now, if something is near to -1, does that make it weak or strong?
Strong.
Strong.
And so wouldn't it be our first guy? Why? Why strong? Because it's near -1. Why negative? Because it's -1, right? And linear, they're all linear, right? Okay. Suppose that the R value was near to 0, right? 0.3 or something. Say again? Fourth one?
Number 4.
Yeah. Weak, or it isn't even linear. Would we agree that near 1 would be strong and positive? So I would choose that one. If you're near 1, aren't you strong? Right, like 0.9 is near 1, right? You're strong and you're positive and you're linear. Right, here are 2 bunches of questions, essentially the same ones. And we're going to choose between moderate, low, or no linear correlation, right? So, A, no correlation, high, or you can choose moderate or low. What do you think A looks like?
Moderate or low?
Agreed. Let's hold off for B. C, which is this guy. I would say high. I would probably use the word strong, but that'll work. High. Would you agree it's pretty good? Nice and tight. Skinny sausage. Isn't A a fat sausage? C is a skinny sausage. Now, what do you think is going to happen to B?
That doesn't look like a sausage.
It isn't even linear, so no. Right. We got it? High or low or moderate should only be used for linear in these questions. How about this guy, and this guy? Okay. A. Can you see a sausage? Would you agree it's a really fat sausage? Is it a really fat sausage that is negative direction? So I'm going to have to try and figure out what that is. In this case, the only thing we need to do here, and I'm going to disagree with them, but since I only have a choice, I have to pick moderate. I would have picked weak, but he never gave me that choice. What do you think I'm going to pick for B then?
High.
Okay. What do you think I'm going to pick for the mess in C?
No.
Okay. So, pretty straightforward. Now, here we have some stories, and we are going to look at them, and then see this bit here about the lurking variables. You know, like I went and said wealth, and the one after that, didn't I say the children's age, and all those kind of things. I like these questions. They're kind of open-ended, so there's a lot of possible answers and different ways of phrasing it, but that's fine. Over the past few years, there has been a strong positive correlation between the annual consumption of diet soda and the number of traffic accidents. Right, so along the x-axis is how much soda is drunk a year, right? And along the y-axis is how many accidents were in that year, right? Whatever that would be. Do you think increasing the consumption of diet soda causes traffic accidents? Please say no. Agreed? But we have a choice of what to describe that to be. No, a strong correlation implies causation, or no, a strong correlation does not imply it. I would say in this case, that one, right? You know, the book kind of does things their own way, but that's what we're getting at, isn't it? Like my silly stories. In the past 10 years, there had been a strong positive correlation between teacher salaries and prescription drug costs. I didn't know that. I'll take the word for it. No, it's a no. Actually, I only have 3, so only one of them is no, so my life was easy this time. Let's think of lurking variables for this one. Give me a reason why increased soda. Say again?
Cell phones.
They could have seizures.
Right, now they are all true, but the problem with those 2 explanations is you have to tie them to drinking soda. I can't see why drinking soda increases cell phone usage. Not directly.
Alcohol in it?
Say again?
Alcohol?
Oh God, let's not go there, but I guess it could be. Oh.
I would say it's like due with lack of sleep because soda drinks typically have caffeine in them.
So the fact that we're drinking more, the fact that we're drinking more soda is actually a reflection on that we're driving more tired than we used to, and we have to take more soda to keep ourselves going. Yeah, I could go with that. This one I'm not happy about, but it's only one my brain spoke about. Do you know when you've got open-ended questions like this, there's kind of lots of right answers, and there's no guarantee that the one I'm about to tell you is any better than the one you're thinking about. I'm just thinking, if we talk about soda drinking and traffic accidents, is if you're drinking a lot more soda, and this is very tenuous, you might be drinking it while you're driving. And if you drink it when you're driving, you might have more accidents. So maybe people are just drinking more while they're driving. I'm not saying that's a good one. That's the only one my brain's coming up with.
Like if they're distracted, is what you're saying.
Because you got to have one hand drinking. I'm assuming you drink it that way. Oh, this is true. Because my wife likes to drive a lot, actually I just think she doesn't trust me driving. But anyway, she likes to drive a lot. I get to sit in the passenger seat, and so I get to look out windows. I have driven by people who are cell phone in one hand and eating something with their other hand and using their knees to keep on the motorway.
He's living life to the fullest.
Yeah,
I once saw
for the
a
short time that person is alive, I guess so. Yeah.
I once saw a woman doing a crossword on the steering wheel.
Oh, God. Yeah.
YOLO.
I'm trying to remember that saying. There's no fixing dumb, right? I think that's a phrase. There's no fixing dumb. Yeah. Whatever. Okay, let's go for prescription drugs and teachers getting paid more. Can anybody come up with a lurking variable for why those two might be connected?
Inflation.
Our friend
Inflation.
inflation.
Yeah, I'd probably go inflation. You know, every year, actually inflation in the last 4 or 5 years has been pretty low. I mean, for whatever reason, but it's been pretty low. But yeah, typical inflation rates are quite different. Inflation rate is a good measurement of how successful a country is economically. It's not a perfect measurement. GDP is a better one. But do you know countries that have super high inflation? They're almost all of them are in trouble. So you know there's some countries like Venezuela that whatever the price of a loaf of bread is today, in a week from now it'll be double that price. If you do history, you remember the Germany between the First and Second World War had hyperinflation, where things cost 2 million, marks to buy a popsicle. What countries did there is that they just produced a lot of money, right? They printed a lot of paper money, and inflation basically is economics' way of fixing that problem. If you double the amount of money, but you only produce the same amount of stuff, won't the price of everything just double to cope with the fact there's twice as much money? I mean, that's the simplified version of how that works. Unfortunately, some of our politicians, and I'm getting my little dig in here, don't know economics 101. A lot of them just think that money just appears out of nowhere. And so you can spend, like my sister. My sister used to think that as long as she had checks, that she had money. Eventually you've got zero in your bank. So it's not worrying me too much because I'm going to be dead. But you lot are young. And do you know that you have to pay all this money back? Or you can just have inflation and everything doubles in price, and I guess that'll fix it. Have a nice, pleasant thought on that. So you lot are making my life dead easy because I'm getting all sorts of cool stuff for free so that you lot, when you get older, can pay for it. Aren't I lucky? Zoe, you're shaking your head. You don't want to pay for all the good stuff I'm getting today? I'm relying on you lot to pay for my social security. So you better lot get good jobs because I want a good social security payment. And the ones that are in the nursing program, I want you to get get good at your job, because I may need you one day. Well, the thing that are wrong with me. Right, we don't want people to do that. That would be scary. Okay, I promised this, and now you're getting it. See this one little diagram with the table above? We are going to do our diagrams. This is how you do it. Or at least this is how I'm going to try and do it. See if you hit that little dot. When I hit it on this screen here, it's going to be one of these guys. So the first one is 3 and 60. So there's 3, and my eyesight says 60. Gotcha. And the next one's 695. Here is 6. There's 95. Gotcha. This one's 12, 140. 12, 140. 20, 158. Good grief, my eyesight. 158. But there. Ah! Hey, come back. Okay, that's better. And what's the last one? 26, 173, 26, 173 is sort of there. Actually, I'm a little bit out. But if I take that last point, can't I just go and change it to what it should be? Okay.
173, but you're good.
Is it one? Oh, thank you. I don't know why I thought it was 178. Yeah. So if you just put it kind of close, can't you go to that little menu on the side and tweak it so it's perfect? And now you're looking at a scatter plot. Would you say that this correlation is low, moderate, or strong?
Moderate.
Yeah, I'd probably agree. Don't be surprised if the book disagrees with you, because I disagree with them sometimes as well. Would you say it's positive or negative? This I won't disagree with, because I'm sure they'll get it right. Positive or negative?
Positive.
Now, do you see all these funny numbers that they say use your calculator to verify, and then they say find R, and then, you know, this bit here. Let's take you through those steps now. Now, I'm going to have to copy this data so I can do those steps. So it's 3, 6, 12, 20, and 26. And then it's going to be 60, 95, 140, 158, and then lastly 173. Okay, so I'm going to come out and in, and we're going to show you how you can do all that good stuff on the calculator. Right, sorry about the mess, I was kind of fast. Okay, on the calculator, what do you think the first thing I'm going to have to do to get the R value for this thing?
Edit and input your data.
Got it in one. Okay, edit, clear out the old stuff, bring in the new stuff. So I like to do them X's and then Y's. So here goes 3, 6, 12, 20, 26, right? It's not going to take that long. If I move over to L2, we're talking 60, 95, 140, 158, and finally 173. Okay, everything matched nice? Now, we'll go stat. Can anybody remember where the R correlation guy is hiding?
Calc number 8.
Calc, and well done, the 8-bit as well. So will you try and remember to do it as 8? Do you see number 4 looks the same as 8? Do you notice that the A is going to be the X and the B is going to be the Y? And if you accidentally use that one, you will get the R value correct, but what you'll get is 2x plus 5 instead of 5x plus 2, right? You'll get the 2 digits switched places. So since the book wants 8, we'll use 8. And most of you get lucky, you got the menu, so you can just go enter, enter, enter. In my case, I have to do Shift L1, comma, Shift L2. And here is some of the things that we want. I'll just write them down in no particular order. The R value is 0.95 because I'm rounding it off. The R squared value is, well, if you round it off, it's 0.90, which is 90%. Well, that's a pretty good fit, isn't it? 90%, pretty decent. Since Y is going to be A plus BX, won't Y be 63.2 plus 4.6x, right? I've just rounded them off again. Are you happy about how this allowed me to get all this kind of numbers, right? Okay. Now, they also have in this question a whole load of stuff where they ask you to verify things like this and some others. That's not in this menu. You can see it's not there, but we can get it. Hit start again. Go over to calc again. And there's a guy called number 2 variable stats. So if you use 2 variable stats, that one, and I'm going to hit enter again, and I'm going to have to do, in my case, L1, comma, L2. Can you see that I get all that stuff? But if you scroll further down, can you see all that sigma y, for instance, that guy there, sigma y, is 626, and so on. So when you're being asked to find out what the value of sigma xy, sigma x squared, and all that weird stuff, well, actually, if you go through this, there is tons of stuff here that you'll probably never use, right? There's a lot of information in that menu. But what you do want is in there somewhere if you go looking for it, right? There's sigma y and sigma y squared.
Wait, is that called sigma or?
Yeah, sigma is the Greek letter that looks like this. That's capital sigma, and this is little sigma. But they're both called sigma.
Oh, okay.
Oh, sigma just means what you get if you add them all up. So when you see somebody saying sigma x, they're meaning you take your data and pretend your data was these numbers here, and you're adding them up. That's what that means.
And then small sigma is the population
Standard
standard
data.
DP.
Yeah, so that
Okay.
they have nothing to do with each other, right? They just happen to use a Greek letter of the alphabet that has the same name. I guess I could, if I was being careful, say capital sigma x squared, capital sigma y squared, but since I'm lazy, I just call it sigma. So I'm going to now return back to that question. And well, since I've got most of what I need in front of me, with a bit of luck, I should be able to finish the rest of this question off. Remember that 626 guy that I found? You see it's here? So you could check that. Now compute R. In this case, R was 0.95. So that's that done. And as X increases from 3 to 26 months, does the value of R imply that Y should also tend to increase? Right, now in my equation that I had, remember it was 63.2 plus 4.6x. But I can tell that just looking at this picture. As X increases, doesn't Y increase? Would you agree as the X's get bigger, doesn't the Y value also get bigger? It's going uphill. So given our value of R, Y should tend to decrease. Given our value of Y, R, Y should tend to remain. Given our value of R,
we can't see the screen. Sorry, I'm a visual person. I can't see.
You're meant to tell me you can't see this screen. Shame on you. Can you see it now? Are we looking at it now? I'm shouting at you and I shouldn't be, sorry. You're looking at it now. You're allowed to say, no, I still can't see it. If you can't see it, I really do need to know that. You can say it, okay. So what I was saying earlier then is that one of the values I got from that 2 variable stats table was this guy here, and all the others are in there if you go looking for it. This guy is 0.95, we got that, and that's the answer to that question. Now, we have a little bit of time, so I want to try and do a real experiment where we are going to try and do some linear correlation, and maybe it'll work. I can tell you right now that I did this with the night class, and the night class it didn't work, but I have tried this before with other classes and it has worked. So I don't know if it's going to work with you or not. So we're going to have male and female. So I'm going to collect some data, but you have to be willing to share. If you're not willing to share, please feel free not to say anything. So you just basically volunteer it by shouting it out. And what I'm looking for here is a male-female couple. It could be your mum and dad. It could be your grandpa and grandma if they're still alive. It could be you and your partner, as long as it's male and female. We want to keep the way I want to collect this data. And we're going to do a linear regression analysis. And basically, we're going to find R squared in this equation. And then I'm going to look at this. I'm going to try and use it to predict someone. So you want to volunteer, you and your partner, your mum and dad's age, or whatever it is. I'll start the ball rolling. I'm 64. My wife is 60. Okay. Anybody want to volunteer?
32 and 39.
Right. Is the male 32?
39.
Male 39. And the female is?
32.
32. Okay.
28 and 34.
Okay. Who's 28?
Me.
Waiting for 3 more? You can
Male
give your
40.
mums if you want. Your mum and dad's, or if you know it. Or
20 and 18.
20 is which one?
The male.
18. 2 more to go.
70.
51 and 50.
Oh, right. We'll have a 51 first, and then we'll have Josh after this, right? So 51 and 50. Who's the male?
Male is 50.
And last but not least, you were going to say something with 70, I think, Josh, I heard.
My grandfather's 78 and my grandmother's 82.
Okay. So what we have here is a relationship between the male and the female in a relationship, right? And we're going to, if I had time, I would plot that. But let's just do the analysis part. So we're going to go to the calculator, and we're going to see how good that data is to being a straight line fit. And hopefully it's good. By that, I mean it's a nice R value, right? A big R value, something like that would be really good. But we'll see what we get. I'm going to go in. I'm going to clear this data out. And we'll try 64, 39, 34, 20, 50, and 78. It's pretty good. And then the corresponding other side is okay. So hopefully I got that in accurately. I'm going to go to start. I'm going to go to calc in number 8. And the linear regression using the data from L1, which is the males, matching it with the data from L2, which is the females. We get this set of good stuff. Push it a little bit to the side. The R value, oh, well done, guys. 0.989. Would you agree that is strong positive correlation? Right? Now, what does that mean? Well, it kind of means what you think it means. Don't older males tend to marry or have partners who are older, and younger people marry or have partners who are younger, right? That's really what it's saying. And that the relationship is really very strong. R squared comes out about 0.98. So that's a 98% fit, which is just backing up what this said. The A value is negative 7.8 and the B value is 1.1. So that's going to be negative 7.8 plus 1.1x. Now the Y is the female's age. And it's negative 7.8 plus 1.1, the male's age. I'm going to try and risk a prediction. Somebody who's not given me the answer, I want you to tell me the male age of that. Keep the female age for a second. Just tell me the male age. Anybody want to volunteer it? I don't think that is an answer. It sounded like a spring. Has anybody got someone, their grandparents, their next door neighbor? Don't really matter. I just need some data.
29.
Okay, so I got, all right, I heard the 37. That's the first one I heard, right? So I'm assuming that the male in this combination is 37 years old, right? So who was it that said the 37 so I can make sure I get the second number correctly? You've gone quiet, whoever you were.
I think it was a 30 and a 70 something.
Oh, it was a 30. See, I don't want both because that gives the show away. So you got to just tell me one of the two. You're going to tell me the male age of somebody that you know. That's all I want to know right now. And then I'm going to
35.
predict. Right, so I have a male who's 35, and I'm going to use that to predict what the female age is. And let's see how good this model works. Negative 7.8 plus 1.1 times 35. On my calculator then. Negative 7.8 plus 1.1 times 35. And the answer I get is about 30.7. So I'm just going to call that 31. Okay. What was the age of the female? Somebody said 35. What was the female?
We had 30.7.
Yeah, but what is the real age? The person who told me 35 has a female attached to it. I'm not being very clear, am I, today? I am not hallucinating. Someone said 35, didn't they? Whoever said 35, did you have a female age, or were you just randomly giving me a number because you didn't understand my instructions? Okay, what is the female age of that person? If you have one, tell me now or forever hold your peace. In which case I'm going to have to do it one more time. But
I don't have that one, but I have a different example you can use.
Perfect, right. So before you say anything, Jess, this is the story. You are only going to tell me the male age.
Yeah.
I'm going to calculate it, and then we're going to see how good the fit is, right?
Okay,
Well,
do you want me to give you a couple whose age is actually probably going to fit, or give you one that
no,
doesn't
just
necessarily
give me
matter?
one random. I don't.
Okay,
Right, so just tell me a
27.
guy.
27.
Right, so we have a 27-year-old. So according to this, the 27-year-old, my prediction on what the age of the other person is, okay, negative 7.8 add 1.1 times 27, and I get the answer 21.9. I'm going to make a prediction that that person is 22 years. What is she?
She's 35.
Whoa, God. That model shot in flames.
I can give you a different one.
I'm frightened that it's going to be worse. I'm going to pause this for a second. We got a mute. We got some background thumping going on. I might have somebody in the chat. Someone says they have a different calculator. Are you okay with that? Whoever it was that said that question. Right. Okay. It was nice. It would have been really good if I'd got a good match here. Can I just put it down to the randomness of process? I mean, if I'd chosen one of these numbers, it probably would have been a better fit. And I'm assuming that I typed in the right data. I guess I could have screwed up there. So what does that kind of tell us? Well, it means that if you have a good fit and you don't get unlucky with the one person you check, you can do quite accurate predictions on things. So I'll give you an example of a practical use of that. Do you know that if you're a real estate agent and one of the jobs that you might have is that you're going to sell someone's house, and you might think, well, how am I going to kind of guesstimate what they should sell it for, right? And you can go online, can't you go online today and they'll give you an estimate of your house's value, right? And you might think, well, did they just pick it out of the air? Well, no, they collect data on similar houses that are near to you and what they sold for. But aren't some houses bigger than others? And what they found, one of the easiest measurements is you make X the square foot of the house, and you make Y the price that it was sold for.
Can you show us your screen, please?
Yes.
Thank you.
Right. So X is square foot, Y is the price of the house. So imagine I collected lots of data, or as much as I can, they're called comparables. And I collected the data, and 2,000 square foot house sold for 350, another 2,200 square foot house sold for 360, right? I collected lots of data, and I end up with this fella. Right, so imagine we did the analysis and we got nice round numbers like that. Now, Y is the predicted price of the house, and it's 50,000 plus or minus 125 times the area of the house in square feet. So he has a new customer and he says, look, I want to sell my house. It's in Illahee and it's in this part of Illahee. And he says, okay, let me look at the comps. And he comes up with this. This is based on maybe 10 houses that are sold in the last year that are in the same sort of area. And the reason why area is important and why you should only collect your data from the same kind of area is, can you imagine that having the exact same house right by the water, then you move it to right next door to a prison? Wouldn't that exact same house, physical house, be two totally different prices? So the area is an important fact on the price of a house, right? Houses with nice views tend to have, you know, better prices than houses that don't have nice views, and ages and all sorts of things. But area is a pretty good rough and ready guide. And then the guy says, okay, yeah, I got some comps. How big is your house? And he says, oh, well, my house is 2,100 square feet. What do you think I should sell it for? Well, if this is a good model, he would sell it for, I'm saying plus or minus, my apologies, it's just plus 125 times this number. And you got your calculator and you go 50, 1, 2, 3, plus 125 times 2,100, and you come up with $312,500. So do you see, if it's a good model, and a good model means that it tends to predict accurately the results. Now, if you do a scatter plot of houses in the same area, and this is area, and this is price, if the data looks like this, wouldn't you be pretty comfortable that this would be a good predictor? You know, this person's house is here, we're predicting that, right? If he goes and does a comp and he finds out that the data looks like that, can you imagine in this second situation, that would only be a very, very rough ballpark figure? Can you imagine the straight line? Couldn't you be anywhere from there to there, right? So the The number that tells us this should be the R value. Now, that's not all, I strongly suspect that's not all that a real estate agent would do. Wouldn't they probably look at the location of your house and say, hey, your house has got a pretty good view compared to most houses that are being sold. So that's probably worth another 10,000. And your house is a couple of years younger than most of the houses in that area. That's probably worth, 10,000 as well. And they might add or subtract a little bit. Oh, your house has only got 2 toilets. People like 3 toilets nowadays. That's probably going to knock 20,000 off your price. But at least doesn't have a base number that you can add and subtract to maybe tweak to suit your circumstance. Excuse me. Maggie, my dog, wanted out. She was trying to tell us. Are we good at this process, this linear correlation thing, where if you give me enough data, I can create an equation like this? Let's finish off on this fella. It's a good point to finish. 50,000 is the y-intercept. So can you imagine I collected the data and it looked like this? 50,000 would be here. And the slope is 125. If I only focus on this formula here, I'm going to put it up here. Too much going on in my brain here. My dog is telling me it's time for a poo walk. Okay. Right. That 50,000 is telling me something, and so does that 125 in the context of this question. If this was 0, wouldn't the y-intercept be 50,000? So you might think, what on earth does that number mean? You can't buy a house that has 0 square feet. That would be silly. Well, it kind of does have a meaning. Do you know what it's telling me?
Starting price?
Keep going. Of what? It's basically telling me what a lot would cost. See, if I just wanted an empty lot in that area, 50,000.
Oh, okay.
Because isn't 50,000 a 0 house? Which is just another way of saying that. Now, the slope is quite interesting. For every extra square foot, doesn't your house go up in value by $125? If you're ever interested, Zoe, you own your house, I'm being nosy here, or what? Right. I don't know if you ever got this, but did they ever tell you what the price per square foot? I don't want to know that number. It's nothing to do with me. But did they tell you the price per square foot? Right. Our house is 150 a square foot or something like that. Right. That's what that number is. So see, when they do a calculation for a house, one of the things that they do is a very, very rough and ready number is called price per square foot. They just take the price and divide it by the area. And in this case, it's about $125. If you go and look at different places, do you know if you go to California, it wouldn't surprise me at all if some of the houses in California were $500 or $900 a square foot. Right? I bet you if you went to the center of New York, couldn't you get a couple of $1,000 for every square foot? Right? You want a house in somewhere, near Hyde Park or whatever, right? Can you see how that number is, for every square foot, you're going to have to pay a certain amount of money. And if that number is really big, isn't that a very expensive area? And if you wanted to get a house in a place where people get shot at all the time, don't be surprised if that is $10 a square foot, right?